as well as a tale of two problems. So so they're all listed here. I want to start with, in terms of weather modeling, it is the best of times. Our NWP model skill continues to increase year after year. Weather decision makers around the world are trusting meteorologists more than ever. More lives are being saved. We're not evacuating as many people with hurricanes, even when they're really close to the coast of Florida, than we did 20 years ago. So in some ways, we are making big progress. But it's also the worst of times, because our current modeling paradigm is sort of running into the brick wall that is Moore's law ending, as Kelly mentioned in her talk this morning. So right now, there's a lot of efforts to figure out what is the next generation of weather and climate models going to look like, and how can we utilize all kinds of different tool frames, whether it be GPUs or code optimizations or new languages or machine learning, to offer ways to continue to increase the power and skill of our models, while getting around the fact that traditional CPUs are no longer as fast as they used to be. Machine learning is a very promising way to do this. There's been quite a bit of research showing that like going back to like Vladimir Krasnopolsky in the early 2000s, and there's another person at ECWF whose name escapes me at the moment, but they're kind of working in parallel to show that you can emulate numerical model parameterizations at speeds that are like orders of magnitude faster than the original parameterization they're emulating. And so there's a lot of potential for this to, if we can get this to work well, to incorporate this into our weather and climate models and run at higher resolution or with more ensemble members, or to get things that were computationally not possible to run in an operational setting to actually run operationally and approximately. The problem we're running into right now, though, is that machine learning libraries are generally written in Python or C++ under the hood. But most of our numerical models are, especially in the weather and climate community, are written in Fortran. And they don't necessarily talk to each other very well. They can, but it's a non-trivial process to bridge this gap. The kind of you can think of it as like trying to get from London to Paris. There's this English channel of different cultures and stuff that causes problems. So the goal with this project I've been working on with a group of people listed on the first slide for the past couple of years is to look at how we can build machine learning model parameterizations for a couple of different key problems that kind of highlight the opportunities and challenges with this approach. And then how do we put it back into the model and make sure the model actually runs well. So the first one problem we're going to talk about is the surface layer, where machine learning parameterization are trained from observations to kind of minimize the assumptions of this existing Monod-Obukov similarity theory, which is theory but has a lot of empiricalness built into it that opens up room for machine learning and also allows us to bring in observations and potentially build a better parameterization than what's there before. And then with the microphysics problem, this is kind of a more traditional emulation problem where we run our original or basically really complex microphysics code, then use the machine learning model to emulate it and put it into a kind of operational level microphysics code and see if we can get the properties of the more complex scheme running within the current scheme. So first I'll start with the surface layer project. And the challenge with this one is that we have to model the Earth's kind of surface energy balance. Basically, when it's sort of the coupling between the land surface and the lower atmosphere. And in the real atmosphere, basically, you have to deal with radiative transfers. So we have shortwave radiation coming down, being absorbed and re-emitted as infrared radiation. But then we also have, in addition to radiation, you also have convection and evaporation and evapotranspiration in particular that are also transmitting energy from the land surface to the atmosphere and back. Inside our numerical models, this is current, and this is true for every numerical weather and climate model from your big climate simulations down to your LES models. they all have this surface layer parameterization that's kind of the coupler between the land surface model and the lowest model level, but also the PBL scheme. And this coupling can get kind of complicated because we actually are feeding information from the lowest model level into the surface layer, which is then talking to the land surface model, which talks to another parameterization called the planetary boundary layer scheme, that then will actually update the state of the lowest model level. So there's a lot of intercoupling going on in here that in the real atmosphere, it all kind of happens simultaneously. So when we're trying to train our machine learning models to go from one to the other, we have to account for the fact that our observations are covering, or like things are operating on slightly different timescales and orders than they are in the numerical model. But we think that our machine learning model has the potential to take these observations and because the observations contain all the subgrid forcings and stuff that we aren't resolving, that the machine learning model can learn that information and provide potentially a better way to do this. And our current theory depends on stability functions. That these are kind of empirical curve fits that to short field campaigns that were done in Kansas in the 1960s and 70s, and then applied globally. And while it's heavily constrained so that it does work globally, there are parts of the world and various situations where it works poorly, like nighttime or in the mountains. And since nighttime happens everywhere and we are next to the mountains, they kind of are both conditions are of interest to us in trying to improve. And so we got some multi-year data from 2 towers, one in the Netherlands and one in Idaho. The one in Idaho is a bit shorter than the one in the Netherlands. But we can basically use these long records to train a new machine learning model parameterization and then try to plug it back into, in this case, the weather research and forecasting model. To do this, we have a fairly small amount of variables that we're using. We're trying to build solely on what's kind of already used for this process. So we have potential temperature gradients, mixing ratio gradients, wind speed at different levels, Bulk-Richardson number, which is a measure of stability, moisture availability, which is a measure of the potential for plants to evapotranspirate given a certain amount of soil moisture, and then solar zenith angle, because the whole day-night thing is kind of important for this problem. Where we're trying to eventually predict are the momentum, sensible heat, and latent heat fluxes between the land surface and the atmosphere. To get that, there are these scale variables, U star, theta star, and Q star, that you can use to derive everything if you can predict them. So our machine learning model will predict these, and then we will derive all this afterward. And so we just train our machine learning models on observations. Once they're trained and they look pretty good, we plug them into WRF in a new surface layer parameterization, and then we let it interface with the rest of the model and see what happens. We're testing 2 machine learning models for this problem. One is random forest. There's been a lot of talk about neural networks, but also the decision trees and decision tree ensembles are also still quite powerful models and useful for a lot of applications. It's an ensemble of these decision tree models which allow you to basically separate your data into smaller and smaller subsets, subregimes, and then make predictions based only on the data points that end up in that subregime. And if you randomize your data, you get different subregimes and different trees that come out of it. And if you average it together, you get a model that's generally more accurate than any single machine learning model, any single decision tree. We also use neural networks, which basically we're just using dense neural networks, so just kind of the fully connected ones. They have multiple layers, but it's not convolutional. We're not doing any of the other fancy stuff. So these are 2 pretty basic machine learning methods. With the random forest, one particular thing we had to do was limit the depth of the trees because given the volume of data we were giving in terms of number of examples, the trees were growing out really, really large if you use kind of the default settings. And the problem is that when you actually save the trees out to disk, they ended up being about a gigabyte in size, which could be a problem if you try to load it back into WRF or running it at every location on the planet or over a very large area. So by cutting letting the trees only grow out to a certain distance, we basically have a model that's only megabytes in size, and that's a little bit easier to load and carry around. Some kind of initial offline results. if you look at the R squares for the different models, which is kind of in blue on the top and bottom here, this is for the temperature scale, and this is for the moisture scale. The existing Monod-Nabokov similarity theory is in the middle, random forest on the left, neural networks on the right. We see that in terms of both R squared and mean absolute error, the machine learning models are doing better. Some of the biggest differences are coming at night. If you they both do pretty similar during the day, but at night you get a lot more higher error points, especially with temperature scale, compared with the random forest and the neural network, which tend to compress things. They are both kind of underestimating some of the variability in the system, which is potentially a problem that I'll touch on later. And we also see a more dramatic improvement for moisture scale because the current approach requires basically uses information from the temperature differences to assume those things apply for moisture, which in observations they don't always do so. We also cross-tested our models, so we trained the models on each site and then tested on the other site. And for friction velocity and temperature scale, we don't see much of a decrease in performance. For moisture scale, there's definitely a much more dramatic increase because Idaho is in the desert, Kabah is in the Netherlands, which is by the coast and is quite moist. So there is definitely some data divergence there, and you see a larger error difference because of that. But in both cases, they're actually both outperforming even with moisture scale, we're getting better scores than we did with, for either one than we did with the original InMo similarity theory. So offline, things look great. But now we have to actually put this back into WRF. And we're going to focus on the random forest part first for this. Obviously, we could try to call Python from Fortran, but that adds a bunch of dependencies and potential bottlenecks. But random forest is a relatively simple model. So, and in the scikit-learn implementation of random forest, you can actually access the data store is kind of a big table. So let's just save each tree out as a big CSV file, and then it's pretty easy to read a CSV file into Fortran. So let's do that and then create our derived decision tree type that just has basically all the different variables that we care about as sort of this derived type. And then our prediction, this is the whole prediction loop for a single decision tree. Basically, it's just kind of going through the tree, and if it's a leaf node or not, then we either go down to the next node and we kind of loop through this until we reach a leaf node. And so, yeah, it's a pretty easy thing to code up. And then to do the random forest part, you loop through all the decision trees and average it. So you can even potentially parallelize this if you wanted to. It's scalable, but it actually runs pretty fast just with this kind of basic code. So we put this into basically into the WRF, and we're testing it in single column model mode first. This is probably not relevant to the audience, but we're using kind of a big boundary layer case study for this, and the YSU boundary layer scheme and the slab land surface model, which is a relatively simple one for our purposes. And so we can show, here's a time series of the different variables from the different models. We see with friction velocity that we're getting a pretty similar trajectory between random forest and WRF, except random forest is a little more jaggedy. The magnitude is also a bit lower for random forest compared with the Monod-Nabokov similarity theory. We also, some of the biggest differences we see are with the temperature scale and moisture scale. So with the temperature scale, we have higher values of theta star at night, and then we actually the random forest seems to struggle with going from night to day. It makes the move, but then when it gets near zero, when it shifts from, when it's positive, it's stable, and when it's negative, it's unstable. When it gets near neutral conditions, it has this little step, and then it finally, okay, I'll go over. And then the second day, it kind of bounces around and then overshoots, and then kind of get the normal span. So we're still working on how do we get through this night to day transition smoothly and accurately. But so these are kind of some of the problems you run into. Everything looks good offline, but then online you start running into some of these temporal dependencies and other weirdness that can be problematic. If you look at the actual boundary layer, we can see that in this case we actually do recreate the boundary layer diurnal cycle for the most part, which is a good sign. Although the random forest boundary layer is much the stable layer is much shallower compared with the Mononovikov's version of it. Which one is correct is not 100% clear yet, but this is kind of analysis we have to do and repeat on to get to a good result. And some of this we actually may need, like I'm just using an off-the-shelf random forest neural network for this problem, but maybe we need to add more physical consistency checks or look at multitask learning or some other paradigms to get better results. Or maybe there's some other things that we need to do that I haven't really thought of yet. Moving on from the surface layer to microphysics. The problem we're trying to emulate here is that going from cloud, going from cloud water to rainwater is one of the more uncertain processes in our models. It is possible to model this using the actual this thing called the stochastic collection equation, where you actually model the interactions between cloud droplets and raindrops and cloud droplets colliding with each other. But it's really, really expensive to do that in a model, so we can't do that in a climate model. We have to approximate it somehow. So currently it's done with like kind of a curve fit to this sort of a bin microphysics scheme, which is kind of can more accurately represent the interactions between cloud and raindrops of different sizes. You take what kind of constants that were fit to something like this that was run like in a single column simulation, and then you build a parametric bulk parameterization to run the actual climate model. For our part of this experiment, we're modeling three processes in particular. One is autoconversion, where we have two cloud droplets combined to form a bunch of cloud droplets combining to form a rain droplet. You also have accretion, where you already have raindrops, and then the cloud droplets run into them, and then the rain droplet gets bigger, and the cloud droplets go away. You also have self-collection, where there's no cloud droplets involved, but there are two raindrops are colliding and making a bigger raindrop. And this is all kind of one of the interesting challenges with this is that it's a conditional process. So this happens sometimes, but not always. And one of the challenges with, say, using a neural network emulator for this is that neural networks assume everything is nice and smooth for the most part. Your domain is continuously differentiable. But in this case, we have some very big conditions sometimes, and then other complexities like sometimes our one process will happen like autoconversion or accretion will generally be happening if you have enough cloud water and enough rainwater. But if you don't have, it's just rain falling in a grid cell, then you may only have self-collection happening. So there's no, so some of these some parts of these processes are not changing. So in order to get around this, we train a bunch of different neural networks on this. We have the conditional neural networks, and then if they determine that a non-zero tendency is happening, we then use a second neural network to predict the non-zero tendency. We can kind of cheat on mass conservation by assuming that if there's a non-zero QR tendency, that it will equal the inverse of the QC tendency, which is the cloud and rainwater mixing ratios. So that makes things a little bit easier. For our data, we're using CAM6. We ran for 2 years. We have it output the inputs and tendencies from this part of the microphysics scheme and save that into a bunch of netcdf files, which I then convert to a bunch of CSV files, which then we train in TensorFlow, Keras to do our neural networks. Here's our kind of setup. We have all of our 3 classifier networks, 4 regression networks, because one of the tendencies has a positive and negative exponential kind of tendency. Here's all the gory details. We're using ReLU activation functions, which I'll return to in a little bit. Here's our kind of results. The accuracies from a naive perspective look really good. We're getting 98%, 99% accuracy and basically predicting these not zero or non-zero tendency, which seems great, but even in a climate where we have millions of grid points, having 1% of them have the wrong tendency could cause problems that might propagate throughout the system. So this, while it seems good, it may not be good enough. We can also look at our histograms of our tendency errors when it is non-zero, and we see that this is on a log scale. So the vast majority of our points, we're getting really close to accurate. We're getting really high R-squareds and fairly low MAEs. But if you look at the full spread of values, we are getting some tendencies that have, and this is on a log scale, so these are errors that are kind of orders of magnitude off from what the actual tendency was in the model. And that's definitely a bit concerning and might be problematic in some extreme cases. But like offline, it looks pretty good. So how do we get this back into CAM and CASM and run? I again adopted a similar approach here to what I was doing at the surface layer. This time we wrote a dense neural network inference engine. We saved the neural network rates from Keras into a netcdf file, and basically instead of using the full Keras HDF5 representation, I stripped it down to just the weights and the important information. And so you can basically just have a list of these dense types, and then you just iterate through it as you're doing your inference, and do some map moles, and you're done. And you don't have to worry about calling TensorFlow or anything like that after you've done the training. So what does this look like in practice? Well, when we run on the training climate, we are basically not getting any slowdowns from, it's not running any faster than the bulk microphysics scheme, but it's still running 3 times faster than the bin scheme it's emulating. So we're getting a speed up there. If we run with the ML emulator in the training climate, it runs for 9 years, fine. This is just as long as we've run it so far. But then we've also tried a couple sensitivity studies. So if you're at Oxford, this is kind of the update since then. We run the ML emulator with a +4 degree Celsius SST pseudo global warming scenario. It runs for 4.5 years before the model blows up. In this case, it blows up in the land model of all places. So even though we're modifying one little piece of the microphysics scheme, it's causing some kind of feedback or biases that are likely affecting the radiation and some other things that affect the temperatures that then maybe I don't know if we're freezing or burning the planet, but it's one of the two. And finally, if you do pre-industrial aerosols, it only runs for 18 months before blowing up. So there's still some big biases that we haven't addressed yet. One of them is just there's more clouds in the machine learning emulator. And we can kind of look at some of the sensitivities and see that when we try to extrapolate, we just keep going off linearly in different directions, which may be a problem if in the real microphysics, it's just like shutting off at a certain point or not doing this linear thing. So we need to look at other ways to extrapolate. I wanted to end with this, the kind of other approaches, since my time's running low. So the Fortran inference approach, I think, is really great for separating out the concerns of the machine learning training and the Fortran model running without any extra dependencies, except that if you want to, say, put a deep learning model or like a convolutional network in, you're going to have to code it up in Fortran, which is possible, definitely, but is going to be a bit more labor intensive and may not work in, say, Fortran 90. It might be easier doing like Fortran 03 or 08. So that's an issue. You also can't do online training if that is a concern. There are some ways to pass information from Fortran to Python using things like CFFI, which Noah Brenowitz wrote a nice little blog post about. And that can allow you just to give Python access to the data inside the Fortran model. And I think there's some other ways to do this, and I think there's other groups here working on that. But then you have to run the Python alongside your Fortran model, which could be problematic for various reasons. And finally, maybe what we really need is something that can go from Fortran to the C++ libraries directly that are underlying things like TensorFlow or MXNet or Caffe or whatever. And maybe if we can build this, we can then access libraries or build networks of arbitrary complexity, do online training, do all the things we want to do. But the problem is this doesn't exist yet, so we need people to work on it and move this forward if this is the route we think we should take. So here's my summary. I'm happy to take a few questions.